Hey, Calculus, we're going to go ahead and talk about 9.2 today, the nth term test for divergence and geometric series. So I'm going to go ahead and flip my camera around so you can see the notes. Okay, so when we're talking about the nth term test for divergence, this is going to be very similar to what we did last time with taking limits to see if something converges or diverges. The first thing we want to do is find the partial sums. Okay. And sum is the big word here in that a series is basically a sequence that we are taking the sum of. When we're asked to find a partial sum, in this case, the fourth partial sum, we're looking to add up the first four terms. So in this first series, we have 1 over 2 to the n, with n starting at 1. So my first term is a half, a fourth, an eighth, and a 16th. I'm going to add those first four terms together to find the fourth partial sum. Of course, you need a common denominator, and we'll get 15/16. This next one, we have the summation of 1 from 1 to infinity. The first four terms are all just 1. So I'm going to add 1 4 times. And so my fourth partial sum will be 4. In this third one, we notice we have an alternator, that -1 to the n. So and we're starting also at n equals 3. So our first term will be -1/3 plus a fourth minus a fifth plus 1/6 for a fourth partial sum of -7/16. These properties down at the bottom are very similar to the limit properties. I can multiply through by a scalar. I can add or subtract two series and their sums will be added or subtracted. And that's subtracted there. Okay. On the back side is where we get that nth term test for divergence. Again, this is very similar to what we did last time. We're going to take the limit of the sequence or of the series as n goes to infinity. If we get 0, or I'm sorry, if we get something that is not 0, it diverges. If we do get 0, it could converge, it could diverge. We just don't know yet. The test is inconclusive. We will need more tests to prove if it converges or diverges. Right now, we don't know. So for 9.2, we'll say inconclusive. As we get through 9.6, we'll have covered 9 tests. And so you should be able to use a different one to figure it out. Okay. So this first one, we have the limit of 2 to the n as n approaches infinity. We will get infinity for that. Infinity is not equal to 0, so it will diverge by the nth term test. Okay. It's important to note that we write either diverge or converge, and then what test we are using. This next one, we're taking the limit of n factorial over 2 times n factorial plus 1 as n goes to infinity. If we were to just take the limit right now with n going into infinity, we would get an indeterminate form. So we know we can use L'Hopital's rule. We don't know how to take the derivative of a factorial though, and that's okay. What we know from L'Hopital's rule is that if we take the ratio of the coefficients or the leading coefficients, we will get that derivative. So our leading coefficients are 1 over 2. So that's going to be my limit. 1/2 is not equal to 0. So again, we get divergent. This last one, we have 1 over n. So we're going to take our limit as n approaches infinity. If we plug in infinity, we will get 1 over infinity, which is of course 0. So this is the one where we have an inconclusive test. Okay. We'll take a little break for a minute. And after a little break, we're going to take a look at geometric series. Geometric series take the form a times r to the n. So a will be a constant, r will be some kind of number raised to the nth power. That n is what's changing from 0 to infinity, or from whatever number to infinity. Okay. And a is just being multiplied by that. We're going to take the absolute value of r. If it is between 0 and 1, it converges. If it is greater than or equal to 1, it will diverge. So this first one, we want to take the absolute value of r, that is 3/2, because 3/2 is what's being raised to the nth. 3/2 is, of course, greater than 1, so the series diverges. Again, I'm not just writing diverges, I'm telling what test we're using. In example 2, only the n is being raised, or sorry, only the 2 is being raised to the n, so that 3 can come out in front. So 3 is my a, 1/2 is my r, and of course n is n. So the absolute value of r is 1/2, which is less than 1. So this will converge. This next one has got a little bit of an interesting thing going on in the numerator. We've got that subtraction. Of course, it is over a common denominator, so I can break it up to 2 over 5 to the n minus 3 to the n over 5 to the n. And just like we did over here, we can rewrite this. So 2 times 1/5 to the n. These are both to the n, so we can write it as 3/5 to the n. And now I have two r values. So I have r is 1/5, which is less than 1, and r is 3/5, which is less than 1. Since they both converge, the original series will converge. If one of them diverged, the whole thing would diverge, because we would have infinity plus or minus some other little constant, which is still just an infinity. In number 4, you'll notice it's raised to a negative power, which means we can flip what's inside. So we can say this is pi over e to the nth. Okay. Pi is about 3.14. E is about 2.7, 1828. Pi is bigger than e, we know that. So this is going to be greater than 1. So this will diverge. Okay. This one, we have 1 plus k over n to the nth. These n's are the same value. We know that n is starting at 0 and will only be positive values. So everything is kind of depend on what k is. Okay. If k is less than 0, this will be negative values. And 1 plus a negative value will be less than 1. So it'll converge. If k is greater than 0, this will be another positive value, and we'll have 1 plus a positive value, which is bigger than 1. So it will diverge. The absolute last thing we want to look at is how to find the sum of a geometric series. We're going to use this formula, a over 1 minus r. This will only work if we're starting at n equals 0. So if you'll notice in 3 and 4, we have n equal 1 and n equal 2 as starting points. We'll have to figure out another way to kind of work around that. Okay, so this first series we've seen before, we rewrote it on the first page as 3 times 1/2 to the n. So we know a is 3, r is 1/2. We can plug that into our formula. So we have 3 over 1 minus 1/2, which is 3 over 1/2, or 6. So now we can say this converges to 6. Okay, so geometric series, we can actually figure out what value it converges to. We rewrote this one on the first page as well, so that it was 2 times 1/5 to the n minus 3/5 to the n. again, I'm going to have two parts here. So I'm going to have this A and R. Because this is a subtraction here, it's going to stay a minus here. Remember those properties we looked at on the first page of notes. A is 1, R is 3/5. We get 5/2 minus 5/2 or 0. So it does converge to 0. This next one, we have an R value of -1/3 and an A of 1. Here, it doesn't matter if the R value is taken with the absolute value. In fact, we don't necessarily want it to when we're plugging into our sum formula. So we have 1 over 1 minus -1/3, or 1 over 4/3, which is 3/4. Remember that this series started at 1. So I need to find the 0th term, A naught. The first term of the sequence, if I were to plug in 0 for n, would be 1. And I need to take that out from my sum since it's not included. This starts at 1, not at 0. We're going to take this out. So we're going to say 3/4 minus my A naught term of 1, and we'll have -1/4. So the series converges to -1/4. Okay. This last one, same thing. We're going to go ahead and rewrite it to start. So like that. A is -3, R is 1/4. We can find our sum. Okay. And we also know we're going to have to find, since this starts at n = 2, the 0th term and the first term. The 0th term is -3. The first term is -3/4. And we're going to take those out of the sum we had already found. Okay, so we're going to subtract those out. When we do, we're going to get a -1/4. So we'll say that this series converges to -1/4 as well. Okay. Homework will be 9.2 on WebAssign, and we will go from there.